All right, so before we get going here, hopefully everyone got the memo before class on Wednesday that we're going to cancel because of dialogue days. I didn't realize they were needing to use this room. So puts us a little bit, behind. So that Excel assignment that was due next Wednesday, I've kind of changed the date to be kind of Friday by the end of the day next week. So we probably won't get through the Excel part today, but Monday for sure, we'll probably do confidence intervals in Excel. So after Monday's class, you should have enough to kind of start tackling that. It's really not too bad once you see it done. You should be able to do that first part though. I would suggest doing that now so you don't have more kind of work to do next week when you have something kind of new. So that first question, I guess, is probably more than a third of the assignment. So you can get, probably a third to a half of it done before seeing what we do on Monday. And then after Monday, kind of everything we need to do to kind of finish that up. Okay. I don't think other than that, I have anything. Are there any questions for me before we kind of jump into the things here today? All right, so we left off. I kind of showed you, what happens with those sample means. We talked about kind of using different sample mean values and figuring out the probability I see something above or below that. So we're going to start out today talking about the sample proportion and then kind of switch over to confidence. So right over here. So what we were doing last class was thinking about the distribution of sample means. Okay. So we had this distribution of our sample means, and we said it'll be normally distributed as long as we have a sample size over 30. The mean of my sample means is just that, whatever the population mean is, and the standard deviation was the square root of the variance, whatever variable I sampled from, over my sample size. So I could calculate this ahead of time, or kind of plug that formula in and kind of do it all at once. Right? And this, right, became just my that population. So with my sample proportion, it's going to follow a really similar format. I'll grab this as I start talking through this because I think I've got something up here. So we go back to the binomial, try to give you a little bit of insight here. Remember, when we're looking at binomial distribution, that was just a bunch of ones and zeros. So when we're looking at a proportion, and going back to Monday's class, we looked at that maternal smoking variable. It was just a 0 or 1. So all the mean was telling us was the proportion of women who smoked during pregnancy. So for the binomial, we kind of think about 1 as being someone smoking, 0 not. The number of people out of n who smoked, we said, was going to be equal to this. Right? Well, if this represents the number of people who would smoke, how would I turn that into a proportion? Just divided by the total number of people that there are. This cancels, and what we end up seeing is kind of the mean. When we're looking at a proportion, it's going to be whatever that true population proportion is. Right? So when we take a sample and we observe a sample proportion, just like the sample mean, we know those sample proportions, as long as we have a sample size over 30, will be normally distributed. We kind of saw that with the maternal smoking variable. It's just that now the mean of my sample proportions, well, it's just going to be centered around whatever that true population proportion is. We think about the variance for my sample proportion. Well, we know that the variance for that binomial was n times p times 1 minus p. Well, a similar idea, that's the variance for the number of successes. So if we want the variance in terms of a proportion, we would just divide that by the total number of kind of observations and trials, and we're left with the variance of my sample proportion. Sorry, not my sample proportions. The variance of whatever that true population proportion is just going to be equal to p times 1 minus p. So it's almost like the variance of my population proportion, that would just be my numerator. right? Because this variance represented the variance of whatever variable x we were sampling from. This represents the variance of p, that thing we were sampling from, to get our proportion. Okay? So our z-score equation for our sample proportion will follow a similar format. Oh, sorry. Where we're going to take some value for the statistic that we're interested in, subtract the mean of that statistic, and divide by the standard deviation of that statistic, right? So same format. It's just that we're looking at a different statistic. It's a little bit different because between 0 and 1, the mean, right, can be negative, can be really high. And if we just plug in what we know here, to turn any sample proportion that we find into a z-score, well, we know the mean of our sample proportions was just whatever the true population proportion was. And the standard deviation of our sample proportions be the square root of whatever the variance was, which we know is p times 1 minus p, divided by, right, just like with the sample means, our sample size. So it's really the same format. Remember what's in the denominator here just represents my standard deviation of my sample proportions. But it looks like a little bit different of an equation because to calculate the variance of the population proportion, it's going to be different than how we calculate the variance from that sample. Or at least we have a way in which we can calculate. So, right, we've got the mean of our sample proportions, the variance of our sample proportions. From here, it's just a matter of following that same format of a z-score. Remember, we subtract the mean, divide by the standard deviation to turn different values into z-scores. Yeah.
Why did you always divide by n?
So remember when we were looking at the distribution of sample means? This was like the idea that if I think about the distribution for my sample means, if my sample are only of size 1 or 2, well, I could see a whole bunch of different, like maybe income values. Whereas when I start looking at sample means over 100 people, well, the outliers there kind of get averaged out. So the sample mean values I see have a much kind of narrower distribution or a much smaller variance. So as I was increasing n, that was decreasing the variance or standard deviation of my sample means. Here it's the same idea. If I was to look at, let's use the maternal smoking one. If I only do samples of size 1, well, I could see sample proportions of 1, right? Really, the only ones I could see there would be 1 and 0. So I'm going to have a really wide range. If I start taking samples of 100 people, it's very unlikely I'd see a sample proportion of people who smoke while pregnant to be 0.9 or 1, right? It's going to be much, much lower, closer to that true population proportion, which I think was like 0.18 or something like that. Right?
So for that variance there, would you divide by n?
So we divided the variance for our binomial distribution by n because we think about the binomial is really what we're using here for proportion. It's just that that's the mean of the variance for the number of successes. We're looking at a proportion, so we're really looking at, you can kind of think about it as the number of successes out of the number of trials. Well, we know the number of successes is n times p, the number of trials, which is represented by n, and that's why, and the same thing for the variance, we would divide the variance of our binomial by n, and that's why we're left with p times 1. Good question. Any other questions on this? So slightly different equation for our z-score here. I'm kind of just writing in different ways. But really, once we have that z-score, the process of what we've been doing is exactly the same. So we've got this z-score equation. Let's work through a problem, right? So as long as we have a sample size over 30, we know everything over there is going to be true. All right, we kind of proved that to ourselves last class we did. So let's say I'm flipping a coin and I would flip it 100 times. Right? What's the probability I get 55 or more heads? Okay. Well, if I think about the proportion of heads that I'm going to see, right? What would that distribution of my sample proportions look like? Well, I know it's going to be centered around that true population proportion. If I'm flipping a fair coin, the population proportion, if I flipped it an infinite number of times, would just be what? The proportion of times it's going to come up heads would be 50% or a proportion of 0.5. So proportions are kind of like, I mean, they're not necessarily synonymous with probability, but it's the same idea, right? The proportion has to be somewhere between 0 and 1. Okay? We could even kind of think ahead of time. I could actually come up with a standard deviation on my sample proportions as well. I know that that's just the square root of population proportion, so 0.5 times 1 minus that population proportion, divided by my sample size, which here my sample size would be what? Flipping the coin 100 times, right? So what would my sample proportion, or this kind of cutoff value that I'm interested in this problem? Well, if I want to know the probability of seeing 55 out of 100 or more come up heads, what's my sample proportion going to be? I saw 55 heads out of 100 coin flips. That is a proportion of 0.55. What did you do there? You took the number of successes over the number of trials. So we're going to be interested in seeing 0.55 or anything greater, right? Well, once we turn this into a z-score, right? So we've started out with this normal distribution. We want to standardize that value, right? And then we could look that value up in the table. The table is going to tell us the area to the left. We want the area to the right, so we're going to have to do what? Subtract that probability from. So we just start plugging our values into that z formula, right? I have the cutoff value I'm interested in is 0.55. Subtract the true population proportion, so subtract 0.5. And if I calculated this ahead of time, I could actually just go ahead and plug that number into my denominator, right? This is the standard deviation of my sample proportions. So if I calculated that ahead of time, I could just plug it in here. Or I could do this kind of all at one time in one formula using that bottom form, that z-score or z-value formula. So if I do this, right, I end up finding a z-score of 1. Okay. So I'll look one up in that standard normal table, find the area to the left. So kind of go through this process just because we're still getting used to kind of using this table. 1.00, that z-score corresponds to an area to the left with a probability of seeing a z-score of 1 or anything lower, 0.8413. Okay. So we found 0.8413 was right here. I wanted the area to the right of that z-score, so I subtract it from 1. Now I'm done. All right. What's that? 1.1587. Any questions over anything in this process? Understand this? Understand what formulas I was using over there on the left-hand side? I was kind of showing you this one from last class. So I'm going to have you guys work on one, and then we'll kind of talk about it here. So a very similar example. You're still working with a fair coin, so hopefully you know the population proportion has to change. That should still be 0.5. Now I'm asking you, what's the probability you see 66 or more heads out of 144 coin flips? So your sample size has changed, right? Your sample proportion is going to be different from the previous example. Right? But if you kind of graph this out, right, kind of draw it out like I did, you'll probably be able to realize you can rule out a couple of these answers. And then to kind of choose between the last two that you can't rule out, you have to calculate that z-score, look it up in the table, find the area to the left. Here you want the probability of seeing more than 66. So once you find the area to the left, you'll have one more thing to do to kind of find that area to the right. Okay. So give you guys a couple minutes to kind of work on this one. You talk with people around you, work with people around you, make sure you kind of are trying to figure out what points are kind of hanging you up or what are the hard points. And we'll talk about it here in 2-3 minutes. Go for another 30 seconds here. All right, if you haven't gotten an answer in, take your best guess here. Got 26, 27 people. We got an answer in? Okay. Any of those using Reef, is it coming up okay? Yes, okay, I'm gonna close it out. So we're thinking about this one. What's our sample proportion here? Sample proportion, our sample size is 144. What's our sample proportion, this p hat? Not quite. All right. So I've got 66 out of how many? Not 100 anymore, but I've got 66 out of 144. So that ends up, what's that going to be? Something below 0.5. 0.458. We'll kind of round it there and just kind of write that. So I know that I've got a sample size over 30. So my sample proportion should be normally distributed. They're normally distributed around wherever that true population proportion is. I kind of mentioned at the beginning of the problem. It's just a fair coin, so we know the population proportion should be 0.5. I'm interested in finding the probability of seeing 0.458 or anything greater. So right away, I know that probability has to be greater than what value? Has to be greater than 0.5, right? Because the area to the right of the mean is 0.5. So if I'm looking for something that's to the left of, even further to the left of the mean, has to be an area of greater than 0.5 to the right. From here, so I can rule out C and A, right? So I know it's going to either be B or D. From here, I'm going to turn that value of 0.45 into a Z-score. How do I do that? Well, I'll take my sample proportion of 0.458, subtract that population portion of 0.5. And now here, where before I kind of showed you could calculate that standard deviation of our sample proportions ahead of time, I could actually just plug it all in at once. So 0.5 times 1 minus 0.5 divided by my sample size of 144. This is how I'm coming up with that Z-score for my sample proportion. If I do this, what did anyone get this here? Should be approximately -1. Yeah, it should be approximately -1. Okay. So to get this entered into our calculator correctly, it should be -1. Like I said, maybe what's helpful, if you want to calculate this value, ahead of time, and then you just have one value plugged in there to the denominator, kind of, less parentheses moving, going on. That can sometimes make the calculation easier, but we should get a z-score of -1. So I look up that z-score of -1 in the table. What area does it tell me is to the left? Nobody got that far? What area is to the left of the z-score of -1? Okay, so go to -1.00. It tells me 0.15 was it 87? I wanted the area to the right. So my final step is I need to subtract that from 1. Right? I get the 0.8413. Yeah. Any questions over any part of the process there? I mean, hopefully we're getting used to this a little bit. Like we did it with just normal variables. Now we start looking at the normal distribution where we're looking at the distribution of sample means, turning those into z-scores, sample proportions, turning those values into z-scores. And really, once we get to that z-score, like the process of looking up in the table and thinking about if I want the area to the left, the right, or in between two values, all of that's the same, right? The z-score calculation is a little bit different because we're interested in different statistics. I say statistics originally, we were just interested in a variable, right? Different values for a particular variable. Then we were interested in probably seeing different values for my sample mean and my sample proportion. Okay. So I think I have all this kind of here. Oh, this is wrong. Probably changed the value and I forgot to change this one. I just saw that. So this should be 0.1587. Let me just save this so when I post the complete version of the slides, we'll have that correct. Okay. Any questions before we kind of keep moving here? We're going to kind of switch gears a little bit. So part of that announcement I put up on Canvas, it said you should have done what before today? Yeah, so in light or in lieu of having class, we had that kind of learn smart or smart book or however it kind of phrases it, to kind of cover this next chapter, which is interval estimation. Okay? So the whole reason why we were doing this sample mean, sample proportion stuff is because we need to understand how those two statistics are going to be distributed so that we can then start to build confidence intervals and do what we'll eventually call hypothesis testing. Okay? So our goal today is to try to at least introduce the idea and understand what's going on with confidence intervals. Right? So hopefully I show it to you in a way that makes sense. So all of these examples were all good and well, but I mean, why are we taking samples if we actually know the true population proportion or we know the true sample mean? What good is our sample there, right? And we already know the population values. Well, we just need to understand something about those distributions because more often than not, we don't have the population mean, right? And the best guess of where that population mean is from whatever sample we took, right? So it's not very likely we can get population data. We'll get sample data and use that sample data to then kind of make an educated guess about where the population parameter is. So I see a sample mean, that lets me guess where the population mean is. I see a sample proportion, that's my best guess of where the population proportion is. Right? So the way I phrase a lot of things today, I'll probably usually just say the mean, but everything else would, the same thing would apply for the sample proportion as well. So we want to make sure that we kind of have unbiased kind of samples. We'll talk about that a little bit. We also want to make sure that we can get a really low variance on the distribution of that sample statistic. Hopefully by the end of the day, I'll kind of give you a reason or you'll be able to kind of imagine why. So the general setup is going to be, we take, a sample, or we don't know where the population mean or population proportion is, so we'll take a sample. From the sample, we're going to get an estimate, and from that estimate, right, our sample mean or our sample proportion, we'll figure out where that true kind of population mean or population proportion lies. We'll skip this slide for a second. I want to go to here real quick, and then we'll kind of go back. Okay? So what we're going to do is take this sample, calculate our sample mean, and then based off that sample mean, even if the true population, like mean income in the US was 50,000, I take a sample and I see 48,000, right? It'd be pretty naive for me to think that that sample is going to be exactly the right, exactly the value of the population, right? It'll probably be close, right? 48,000 is pretty close to 50,000, but it's very unlikely my sample mean will be exactly what the population mean was. So what I'm going to do is create a range of values, right? I'll have an upper bound and a lower bound value and say things like, with a 90% certainty, based off the sample mean that I saw, the true population mean is somewhere in this range of values, right? So maybe I see 48,000. I say, well, I want to be kind of safe. So I'll go 5,000 to the left and the right and say there's a 90% chance that the true mean is somewhere in between 43 and 53,000, right? I'll create this range of values and say with a certain level of confidence, I know that the true population mean is within this range. Now, why or how we know what level of confidence we can say that at is what we'll eventually get to. But for now, that's just our end goal, building this range of values where we can say that based on our sample mean, we think the true population mean should be in this range with a certain level of certainty. Okay? So how do we choose this W is what we're then going to kind of work on. If I go back here, right, when I'm saying that, maybe with 90% confidence, I can say that the true average income is in between 43 and 53,000. Well, I might want to be able to say things with higher levels of confidence, okay? So if with 90% confidence, I can say it's somewhere in between 43 and 53,000. If I want to be able to tell you a range of values where I can say with 99% confidence, it's within this range. Well, one way I can get a higher kind of level of confidence is just make a wider range of values. If there's a 90% chance it's in between 43 and 53,000, maybe it's like a 99% chance it's in between 33 and 63,000. I just make the interval wider. So intuitively, to say things with a high level of confidence, we're going to need a wider kind of range of values. I will kind of walk through the mechanisms when we actually look at the equation for our confidence interval. Behind, we can actually see it play out, that our intuition is correct. To say things with a high level of confidence, we need a wider interval. Right? And we'll walk through exactly what that looks like. So we know the sample mean is normally distributed. So let's make sure I have the right slide here. Okay, I'll start building this. So we know that sample mean is normally distributed around whatever the true population mean is. And we actually can also calculate the standard deviation if we want to. So let's think about this. I've got this distribution of my sample means. I know that if I go out, not just one standard deviation. If I go 1.96 standard deviations to the left and right of that true population mean, I don't know what these values necessarily are because I can't observe the population. But if I were to go out 1.96 standard deviations, I know that the area in these tails, or the probability of seeing something more than 1.96 standard deviation in either direction. Well, if I turn this into a z-score, what would this value have a z-score? Remember the definition of a z-score. It's just the number of standard deviations away from the mean I am. So the value that's 1.96 standard deviations below the mean would have a z-score of negative 1.96, right? It's 1.96 standard deviations below the mean. I can look 1.96 up in my standard normal table, and the area to the left of that z-score I would find would be 0.025. So that's where those two values are coming from. It would just be if you looked up the z-score of negative 1.6 and 1.6 up in the table, kind of find the area to the left of the negative one, to the right of the positive value. We know those areas should be 0.025. So said differently, there's a 95% chance, or a probability of 0.95, that I see a sample mean somewhere within 1.96 standard deviations of the mean, true population. So we know this distribution is centered around whatever that true population mean is, even if we can't observe it, right? We kind of have those areas in the tail now. If I were to see a sample mean that is something less than 1.96 standard deviations away from the true population, right? So let's say I take one sample and it's somewhere in this range, something that's less than 1.96 standard deviations below the mean. If I then build a confidence interval by taking that sample mean, going out 1.96 standard deviations. Excuse me. If I go out 1.96 standard deviations to the left and the right of that sample mean, well, notice it was only like 1 standard deviation below. So then if I add 1.96 standard deviations back to that value, I'd be at a point that's on the other side of the mean. Right? So anything within this range is less than 1.96 standard deviations below. So when I add 1.96 standard deviations to it, it's going to put me back on the other side of that population. So any sample mean in this range, if I build my confidence interval around the sample mean that I see, I know that its confidence interval, right, would include that population mean. If I see a sample mean value over here, right, well, that's less than 1.96 standard deviations above the mean. So when I create my confidence interval, right, by adding 1.96 standard deviations to that sample mean value, adding it to the upper bound, subtracting to the lower bound, well, I'm something like maybe 1.5 standard deviations above. So then when I subtract 1.96, well, that sends me back over on the other side of that population. So for every sample mean value here, that's less than 1.96 standard deviations above or below, I know their confidence intervals. Notice will include that true population mean. Now, if we end up with a sample that's a little bit less likely for us to see, we might end up with a scenario where I see a sample mean out here. Now, when I build my confidence interval around that, well, I'm something like maybe 2.5 standard deviations below. So then when I add 1.96 to get my upper bound, it's still going to be pretty far from wherever that true population mean is. And for every sample mean value out here in my tails, my confidence interval wouldn't include that true population mean. So I know that for 95% of these sample means, when I build my confidence interval, it'll include that true population mean. I know that for 5%, right? 0.025 probability here, 0.025 probability here. For 5% of the sample means that I would see, my confidence interval wouldn't include that true population mean. Okay. Any questions on this idea before I keep going? Just trying to give us a little bit of intuition behind why this is the case. I've got a slide in here that kind of reminds us of that. They wanted to kind of go build it step by step and kind of really try to envision why those confidence intervals would include that true population. So in practice, like if we know this is true, at least for now, take it as given. I actually have a thought experiment in Excel. I'll probably show you on Monday that really tries to solidify this idea too. But if I'm only able to take one sample, and then I build my confidence interval around that, well, I know that there's a 95% chance that I ended up with a sample mean that my confidence interval will include the true population mean. And then there's a 5% chance that it won't. So that's why when we build these confidence intervals, we can say things like, with 95% certainty, and that's coming from because I know this is a normally distributed variable, and I know, when I convert that to the standard normal distribution, I know how this works. 95% chance I see a sample mean that has a confidence interval that includes it, right? 5% chance that I know. So 95% confidence, I'm telling you that the confidence interval I created does include the true population. Yeah.
So are those supposed to have numbers on it, or does it just show like?
So in practice, they would, right? If I actually had the value for my standard deviation of sample means and I had my value for the sample mean, I'm actually going to end up with some numbers for my lower number bound. Yeah. This is just kind of the general, like, why it doesn't matter if we don't have numbers. We know that whatever those numbers end up being, there's a 95% chance that our confidence interval captures with that true population.
Okay.
Yeah, we'll get to an example. So one term that we want to get down here, and it may not be quite clear that we've already been working with it, is anytime we want a certain level of confidence, we're going to refer to this thing called alpha. So the easiest way to think about alpha, this is how I explain it. I'll explain it a couple different ways, but the easiest way to remember, I think, is it's whatever percent is outside your confidence interval in decimal form. So if I wanted the 90% confidence level, 10% is outside that interval in decimal form, that would be an alpha of 0.1, right? 99% confidence level, there's 1% outside my confidence interval, decimal form, the alpha would be 0.01. So that's one kind of easy way to think about alpha. It's essentially the probability of seeing something in the tails, right? Or something outside of whatever confidence level you want. So 95% confidence, there's 0.95 in the interval, which means there's 0.05 outside. Questions on that? And we can work in either direction. And if I tell you alpha, you should be able to back out what the confidence interval is. If I give you the confidence interval, you should be able to back out alpha. All right, that's why it's a 95% confidence interval. You know alpha is 0.05, right? The area outside the interval in decimal form. If I give you an alpha of 0.15, what confidence level would that be? Alpha was 0.15. The confidence level would be 85%. Right. So we can work in either direction. Now, essentially what we're doing to build this confidence interval, like how did I come up with this 1.96? Well, I knew the area that I wanted in the tail, so I just looked that up in my standard normal distribution, because that would tell me how many standard deviations away from the mean I had to go, right? How many standard deviations, 1.96 times that standard deviation, so 1.96 standard deviations to get that area in the tail I wanted of 0.025. Well, what was that area in the tail? Well, alpha was the total area in the tails, but I've always had two tails. I always have two sides of my confidence interval. So alpha over 2 was in each tail. So what this 1.96 value represented was just the z-score that gives me alpha over 2 in each tail. So whatever my confidence level is, I can determine what alpha is. I can then look up alpha divided by 2 in that standard normal table. Now, when I look it up, that's the probability. So I'm looking at those numbers in the middle and then finding the corresponding z-score. So the form of our confidence interval is really just going to be take my sample mean, add to it that z-score for alpha over 2 times whatever that standard deviation of my sample means is. So when we add that z-score, that's giving us our, when we use the positive value of the z-score, kind of like here, that's giving me my upper bound. When I subtract or use the negative value of that z-score, that's giving me my lower bound. But I'm adding and subtracting the same thing to that sample mean. So my confidence interval is built around my sample mean, and it should be smack dab in the middle. Questions on this? We'll keep moving here. So if that's my confidence interval equation, there's actually another way that we can write it. And it's really whatever way is easiest for us to, when we're doing this by hand or computing this. So here's my confidence interval equation. But I have a formula for that standard deviation of my sample means, right? So another way to think about this is, I'll get out of the way in a second. We could use that form, right? So we could break this down to steps and, find this guy first and then plug it in, or we can just do all the work at one time, right? I feel like sometimes when people do that on a calculator, there tends to be some order of operations mistakes that can happen. So usually I suggest like starting out, calculate this ahead of time so that you just have fewer things to enter in your calculator all at once. Any questions over anything here? All right. So where are we at on time? Well, I want to make sure we work through an example, and then I'll kind of come back to this if we have some time. So let's say I've got this hockey puck production, and I don't know, maybe I'm providing NHL or something. So I'm really concerned to make sure that the weight is correct, right? Now, this is where it gets a little goofy. The first examples that we're going to work through with confidence intervals start out where we know the population variance, okay? In practice, that's not going to be very likely. How the hell do I know the population variance if I don't know the population mean, right? It doesn't make a whole lot of sense. But the applications that do make sense are usually when I've got some production process where I know that the machinery should have a certain kind of variation to it. So, maybe I'm looking at hockey pucks. I can't pull every single one off the assembly line, so I don't know what that population mean if I've calibrated it correctly is. But I can pull like 49 of them off the assembly line and look at the sample mean of those 49. And maybe I know the population variance because I know that, the science behind this machinery, it's always going to have a variation of production of X amount of grams, right? So it's a little bit of a stretch, but we have to start out with these, understand these types of examples until we go to more like real world or applicable examples where we only have a sample variance, right? But that'll be kind of next week. So I've got this kind of known population variance of 49. I calculate my sample mean of the 49 pucks that I sampled, and I want to build a 99% confidence interval. Okay? Well, I've got my sample mean. I've got my sample size. I have my population variance. The only thing that I still need to look up is that z-score. Excuse me, that gives me alpha over 2 kind of in each tail. So what I'm thinking about here, when I'm looking up these z-scores, is I want that z value such that the area total in the tails is alpha. So the 99% confidence interval, my alpha would be what value?
0.01.
0.01, right? The percent outside the interval is 1%. In decimal form, 0.01. Or the probability of seeing something more extreme than that z value is going to be 0.01. So I know that there will be alpha over 2. I apologize. I know my t's kind of look like alphas, but alpha over 2 in each tail. So here, 0.01 over 2. Or 0.005. Remember, I'm grabbing this z value, so it's coming from that standard normal distribution. So I go to the table. Now we're kind of using, I shouldn't say we're kind of, we are using the inverse kind of approach now because we have the probability we want to find the corresponding z source. So I go down here. Oh, I need 0.005. Looks like I'm in between these two values. So negative 2.57 and negative 2.58. So I'll kind of use the larger of the two in magnitude or the greater in absolute value. So ignore the negative sign. 2.58 is a little bit bigger than 2.57. So that z-score that gave me 0.005 in the tail was negative 2.58. Now here's where it's a little tricky when we're first starting out. People always want to kind of carry that negative sign with you. But remember, what you're actually doing with a confidence interval is you're going to have two sides. So to get the upper bound, you're going to use that z value. You want to go that many standard deviations above your sample mean, right? So to get my upper bound, I want to go that many standard deviations above my sample mean. To get my lower bound, I want to go the same number of standard deviations but below it. So even though I've got a negative 2.58 when I look this up in the table, those signs are already built into my confidence interval formula. The negative sign, or the negative value, will be the one that gives me my lower bound, and the positive of that same z-score will give me my upper bound. So we found the only other thing we need here is what? The z-score was 2.58. And for that point, it's just like, right, a matter of kind of going ahead and solving this. Now we could have come up with this ahead of time. This one's actually pretty easy. 49 over 49 is 1. The square root of 1 is 1. So here I kind of had an easy example where that standard deviation, if I calculated it ahead of time, would have just been 1. That's pretty easy to plug in, right? But at that point, it's just a matter of getting all those values kind of plugged into our. These are kind of the general forms. If we use our actual numbers, we found that z-score of 2.58. We turn the standard deviation, we calculate the standard deviation for our sample mean to find that's 1. Now it's just a matter of plugging everything into that formula. We add to our upper bound, we subtract to our lower bound, and we kind of, once we get to that point, we're done. We've got our kind of range of values. So in this example, I could say with 99% confidence, the true average weight of these hockey pucks is somewhere between 5 and 10 grams. Now, I'll try to give you a little bit of interpretation here in a second before we leave today of why that could be useful. But are there any questions kind of over the process up to this point? So, one thing that I want to point out here is that we've got this range of values that we can say with 99% confidence the true mean is somewhere in this range. Now, it seems pretty inconsequential if I'm doing something like with hockey pucks. And I've got a couple other examples we'll probably kind of start out just to do some review with on Monday, where we're looking at kind of weights of different things. So a lot of these, I'm trying to use some weight examples. But if instead of hockey pucks, right, this is like the weight of, I don't know, some type of medical device, like, I don't know, even if you want to get the average weight of like stents or something that you're producing, so you want to make sure they're exactly what they need to be. Well, a range of 5 to 10 grams maybe doesn't help me a whole lot, right? If whatever this is, if it's, below, 7 grams, it doesn't work, right? Or you can think about maybe I have the weight of some steel beams that are supposed to support, fill in the blank, some building, bridge, whatever. Well, if I sample some of them and find out that based off the confidence interval, the true population mean isn't above a certain threshold for what those beams need to be, I've got a huge problem, right? So, a lot of the times when it comes to the production of any unit, if we're having like a target weight or like a target number of particles, if we're looking at maybe some type of medication or drug, well then this confidence interval becomes very useful, because if that targeted mean for our product isn't in our confidence interval, we know something's going wrong in the production process, right? We need to alter whatever it is, because we're not actually producing the good that we're wanting to produce. So hopefully, kind of what we can do is get that range to be narrow, right? I mean, it's great that with 90% confidence, I can narrow this down to a range of 5 grams, but maybe I want to make sure that I can narrow down to 2, right? So how can I make this interval a little bit more narrow? Well, we go back to this equation. I'm going to have this slide. We'll probably come back here. Things that change the interval. There we go. We've got 3 things that can change the size of our interval, right? So if we're looking at this equation, if the sample mean changes, what happens to the size of our interval? The sample mean changes, what happens to the size or the width of the interval? Nothing, right? That doesn't change anything about what we're adding and subtracting to that value. It's just going to shift our interval around, right? But it's going to be the same width. So on Monday, what we'll start out with, and I'll walk through each one of these a little bit more independently, is there's 3 things that can change the width of our interval. What alpha level or what confidence level we want, the original variance of the data we sampled from, or our sample size. So we'll walk through how each one of those things changes the width of our confidence interval, and then we'll probably work through a couple more problems. I'll show you how we do this in Excel, and we should be kind of all ready to go for that second half of that Excel assignment. Okay. All right. If you have any questions for me over that Excel next week, please feel free to reach out after we cover it in class on Monday. Other than that, the Connect assignment is due. Yeah. Oh yeah, so I moved the day of that Connect, so the end of the day on Monday. We have covered all the material, so you should be able to work through all those problems. Okay. Have a good weekend, and I'll see you guys on Monday.